mass of 10 kilograms is attached to a hanging spring and allowed to come to rest in its equilibrium position, stretching the mass 12 centimeters beyond its natural length. The mass is then pulled down an additional 4 centimeters and released with an initial velocity of 1 meter per second upward. Assuming no damping, find a formula for the position of the mass after t seconds. Make sure to clearly define your coordinate system. The only difference between this problem and the last example are the initial conditions. Now, y of 0 equals 0.04 and y prime of 0 equals -1. Remember, I decided that down would be the positive direction when I do problems. So since the initial displacement is below equilibrium, y of 0 is positive, and since the initial velocity is upward, y prime of 0 is negative. Our general solution hasn't changed. It's still y equals c1 sine of 9.04t plus c2 cosine of 9.04t, and y prime is still 9.04c1 cosine of 9.04t minus 9.04c2 sine of 9.04t. Applying the first initial condition, y of 0 equals 0.04, is essentially the same as before. 0.04 equals c1 sine of 0 plus c2 cosine of 0, so c2 equals 0.04. In fact, if a system is free and undamped, the initial position will always be the coefficient on the cosine term. Applying the initial condition on velocity, we get that -1 equals 9.04c1 cosine of 0 minus 9.04c2 sine of 0. So c1 equals -1 over 9.04, which is approximately -0.11. If you're looking for a shortcut here, if you call the coefficient on t inside the sine and cosine functions omega, then the coefficient on the sine term is always y prime of 0 over omega for a free undamped system. So our position formula is y equals -0.11 sine of 9.04t plus 0.04 cosine of 9.04t. We could stop here, but if we could write our solution as a single trig function, we would be able to better understand the motion of the mass because the amplitude and phase shift would be apparent. The amplitude tells you how large the oscillations are, and the phase shift tells you whether the oscillations are ahead of or lagging behind a standard sine or cosine curve. We won't actually be super interested in that for this class. To write a function of the form a sine theta plus b cosine theta as a single trig function, we need to dust off some old relics from trigonometry. To write a sine theta plus b cosine theta as c cosine of theta plus phi, we use the formulas c equals the square root of a squared plus b squared, sine of phi equals negative a over c, and cosine of phi equals b over c. If you wanted to write your function as c sine of theta plus phi instead, you certainly could, but the formulas would be a little bit different. For our function, a equals -0.11 and b equals 0.04. So the amplitude of the oscillations, c equals the square root of -0.11 squared plus 0.04 squared, which is approximately 0.12. Finding phi can be tricky. Plugging in our values for a and b, we get that the sine of phi is -0.11 over 0.12, which is approximately 0.92, and cosine of phi equals 0.04, over 0.12, which is approximately 0.33. I'm being a bit sloppy with my rounding. What I should really be doing is keeping all the digits from my calculator at every step and waiting until the very end of the problem to round, but that ship has sailed. Once we have the values of sine phi and cosine phi, we need to identify which quadrant our angle phi is in. In quadrant 1, sine and cosine are both positive. In quadrant 2, sine is positive and cosine is negative. In quadrant 3, sine and cosine are both negative. And in quadrant 4, sine is negative and cosine is positive. This tells us that our angle phi must be in quadrant 1. Why do we care? Which quadrant the angle is in determines how we calculate it. Since we have two equations involving sine of phi equals 0.92 and cosine of phi equals 0.33, we could use either one to solve for phi using inverse sine or inverse cosine. But the ranges of inverse trig functions are limited. The inverse sine function only outputs angles in quadrants 1 and 4, and the inverse cosine function can only output angles in quadrants 1 and 2. What does this mean for finding angles? If your angle is in quadrant 1, both inverse sine and inverse cosine will give you the correct angle right away. If your angle is in quadrant 2, inverse cosine will give you the correct angle right away. If your angle is in quadrant 3, unfortunately, no inverse trig function will give you the correct angle right away. You'll need to modify the output in one of two ways. If you use inverse sine, then the correct angle is pi minus the inverse sine of negative a over c. Or if you use inverse cosine, the correct angle will be 2 pi minus the inverse cosine of b over c. And if your angle is in quadrant 4, then inverse sine will give you the correct angle right away. In our case, the sine and cosine of phi are both positive, so phi is in quadrant 1, and either the inverse sine or the inverse cosine will work. So phi is equal to the inverse sine of 0.92 or the inverse cosine of 0.33, which is approximately 1.2. It's important to make sure your calculator is in radian mode. Calculus is always in radians because the formulas for the derivatives and antiderivatives of the trig functions would be different if the angles were in degrees. Our final answer as a single trig function is y equals 0.12 cosine of 9.04t plus 1.2.